Alright, so today, guys, we are going to look at today we're going to look at the general rules of probability. General rules. Alright. So this lesson is relevant for both grade 10 and grade 11 learners, so no one should leave this lesson. If you are in grade 10, you are in the right place. If you are in grade 11, you are in the right place. Both of you, you are in the right place. Because I'm going to look at the rules of probability. And you cannot afford to not be here when I look at the rules of probability. Yeah. So, the one that is common, that we should all know, is that the probability of a particular event is equal to the number of elements in that particular event over the number of elements in the sample space. That is just probability as a definition. This is the rule that we utilize. So the probability of an event is equal to the number of elements in that particular event over the number of elements in the sample space. That is the definition of probability. Then we have something that we refer to as the addition rule of probability. The what? The addition rule of probability. Thank you, Mr. N. Very earlier on, let me just extend that heart, that language of gratitude. Guys, in my comment section, I have a founder of a maths club. He calls it the Maths Confidence Club. Some of you that have joined in may have seen flyer, you may have seen my status updates on WhatsApp, and then you may have seen there specifically flyers on the Confidence Club. So Mr. N in the comment section, the one who you can see in the comment section, the one who has dished out the rows, he is going to be running sessions on Microsoft Teams, mathematics sessions on Microsoft Teams. And so here on TikTok, you can go and search the Maths Confidence Club. Just if you can, Mr. N, in the comment section, maybe you can just type the name of the the initiative itself, so that you guys can go and look it up. He is offering mathematics, technical maths, and maths literacy. So if you are an individual who is interested in getting ahead of the game, starting term 3 in June already, from the 30th up until the 11th, then Mr. N is your man. I think you can even go to his actual TikTok page, Mr. N, as you can see in the comment section. You can just go on there, and you can, I'm sure in his bio there's also additional information. Venolin, what are you doing here? Literally finished high school 3 years ago. What am I doing here? Well, I guess you are missing high school. It must mean that. Okay, so for the general rule of probability, the first one is the definition of probability. So this here means P. The P means probability. The E stands for the probability of an event. So the E stands for an event. So the probability of an event is equal to the number of what? The number of elements in that particular event, or in other words, the favorable outcomes that we have in the numerator. the favorable outcomes over the total possible outcomes, or in other words, the number of elements in the sample space. So I'm just going to write here the number of elements in the event. So we refer to that as our favorable outcomes over NS means the number of elements in the sample space. Number of elements in our sample space. So in other words, we refer to that as the total possible outcomes. The total possible outcomes. So that is the definition of probability. Probability of an event is equal to the number of elements in that event, or in other words, the favorable outcomes over the what? The number of elements in the sample space. Our sample space consists of the total possible outcomes. Okay, so that is the definition of probability. What we did in previous sessions, we looked at how we can answer questions on probability, and you guys can go to my YouTube channel. I've posted the first 2 videos on probability, which is like the introduction. The first video is like nearly an hour long, and the second video is like 2 hours long, because in the second video what I did is in the live session that I did actual problems. I answered specific problems and I engaged the learners in the live, so that they can actually also feel like they are understanding what I am putting across. Then number 2, we have the addition rule of probability. The addition rule, guys, simply says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So I repeat, the addition rule of probability says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. Now, A is obviously referring to a specific event. B is also referring to a specific event. This or is referring to something that we call the union. The union. All right. That's why if we look at alternative notation that is usually used for the probability of A or B, we can substitute the or with this upside, this U, which stands for union. Now guys, when we talk about things that are united, it's like the total of what we have. All right. So the union is everything. It's like the total, the sum. All right. Okay. All right. I love the fact that Mr. N decided to actually enter into my live using the Mathematics Confidence Club page, so that he can actually be able to, you can see what I meant about this particular Mathematics Confidence Club that I was talking about earlier on. So guys, if you guys want more information on the Mathematics Confident Club and the classes that Mr. N via the Confidence Club, because Mr. N is the CEO of this particular program and initiative that is there to restore the confidence of maths in learners, because I'm sure if you guys have gotten your reports for term 2, or if you were able to actually get your results for term 2, some of you may feel, a lack of confidence in your maths understanding and knowledge. So Mr. N is kicking off an initiative. You guys can go and visit his page. Please, guys, in the comment section, you can see the Maths Confidence Club. Visit his page. He has an initiative starting on the 30th of this month, which is Monday. It will be running up until the 11th. He'll be running classes, guys. He'll be running classes via Microsoft Teams for the respective grades, grade 10, 11, and 12. And he has a team of other teachers that will actually be mobilizing the learners. So to get further information, all right, you can go to the page, Mathematics Confidence Club. You can go and check out the flyers that are there. I think he has his contact details on the flyers as well. If you go to the actual page, and you can contact him personally on WhatsApp, he doesn't mind. You can contact him personally or contact one of his associates. But the number is on the flyers that he has available on the page, and I think on the bio as well. You can also register to be part of the learners that will be getting the lessons starting from Monday, which is the 30th, up until the 11th. And what he wants to do there, guys, okay, is he wants to actually make sure that you get ahead of the syllabus. You do term 3, all right, early, so that you guys can, by the time you go back to school, you are already in the position of confidence when it comes to your mathematics knowledge. There, I've pinned the page, Mathematics Confidence Club. He just said thank you, Mr. Mac, there in the pinned comment. So you guys can click on the page itself. You can click on the link, and on the page, and you can go and check out what he has to offer for all of you. I hope you guys were able to receive that information. You can get further information and explanation on that page, guys. Okay. All right, so that's a little bit on the Mathematics Confidence Club. Guys, we are all here to try and assist, those who need the assistance. Some of you may not feel assisted via my live sessions, but someone like Mr. N via the Mathematics Confidence Club, since he has these Microsoft Teams sessions, you guys may be able to actually get the assistance that you need. And you may be able to actually understand things a bit more. So please do share the Mathematics Confidence Club, even with friends that you have in your respective schools, because Mr. N does not only assist with mathematics only. Those who are probably taking technical maths, maybe you have friends that are doing technical maths, Mr. N helps out with technical maths as well. All right, please, guys. And maths literacy as well. Maybe there are learners who are struggling with maths literacy, grade 10, 11, and 12. Mr. N will help with that as well. His classes are starting on Monday, and it will be very beneficial for those that are able to join those sessions. Please go to I'm just gonna pin the page again, Mathematics Confidence Club. I'm gonna pin it. There it is, guys. Okay, Mathematics Confidence Club. Just go to the actual main page so that you can get access to the information with regards to the sessions that he'll be holding online via Microsoft Teams. And let's go for it, guys. A4 away. All right. Okay, I think that's enough info for now. If there's any questions, you can throw them in the comment section. Mr. N will be more than happy to answer those questions if there's a need. Guys, this session is beneficial for both grade 10s, 11s, all right? And also, if you are a grade 12 learner and you've forgotten the basics of probability, you are also in the right place. So please, across the grades, grade 10, 11, and 12, if you are here, you are in the right place, all right? So let's go back. What were we looking at? We first looked at the definition of probability, the probability of a specific event. Now, You may find that I'm not going very deep because I've explained these things in previous videos. You guys can go to my YouTube channel. In my YouTube channel, I've already posted the first 2 sessions that I did on probability. This is the intro to probability. You can go to my YouTube videos and can watch those sessions that I did the previous 2 nights. So this is my 3rd session, and we are getting into the rules of probability. So I'm just going over what we did as far as the definition of probability. Probability of an event is the number of elements in the event, or in other words, our favorable outcomes from that event, over what? In the denominator, the number of elements in the sample space. In other words, the total possible outcomes. That's how we represent probability. And we did then say that probability of any event, once we get the probability, it will always be between 0 and 1. Okay, and we have a scale that we use, to determine or to check how likely an event is to happen. All right, if it is 0, it means that event is impossible. If it is 1, it means that event, that particular thing happening, it's certain that it will happen. But if it's in between, midway between 0 and 1, like that's halfway, it means that there's 50 chances of that happening. There are even chances of that happening. And then the more closer the value is to 0, it means the less likely it is to happen. And the more closer the value is to 1, it means the more likely that that particular thing will happen. So probability of any event will always be between 0 and 1. You'll never get something that is greater than 1 when you are referring to probability. Okay, yeah. So pretensia mafefe, right? Like I said, I am just getting into the topics in term 3. So I know ATP, you're gonna say it starts with trig. Well, that's great. All right, and I'm just deciding to start with probability. What's nice is that I do this session, it gets posted onto the YouTube channel, so any learner then can go and revisit the lesson at their own time, at their own pace, whenever they are ready to actually confront that particular topic. At the end of the day, when term 3 is done and you have to write your control tests, they will be based on these topics. And the sooner you can have access to the knowledge around these topics, the better. All right, whether you do them earlier or later. All right, okay. So like I said, that is the probability of an event between 0 and 1. Then we have something called the addition rule of probability. So the addition rule of probability is simply this. P means probability. So we have the probability of A or B. And if you listen to me closely, I said A is a specific event. B is a different event from A. All right. So A is a specific event. B is a specific event. All right. You are welcome, Pretensia Mafefe. You are so... I love your comment. I love your comment. You know how I was actually like anticipating you're just going to crush me because I'm starting with probability instead of trig. But thank you so much. Really appreciate the warmth and the kindness in your comment. And I'm glad we've been able to assist you in the manner that we have. All glory be to God. P, A, or B. So probability A is a specific event. B is another event. Or, this or here is something that we call the union. Okay, the union. Okay, or means union. All right, and there's something that we call set notation. Okay, set notation. Now, in the set theory of set notation, instead of using letters and words, we use symbols to denote, certain words. So instead of saying or, we can just use this symbol, which is the U for the union. It's U, all right? And this symbol stands for or, right? So whenever you see P, That means probability, even in the probability topic. A means an event, B is another different event from A, and then or simply means the union, all right? And we can substitute, or we can write or as this symbol in set notation, which is U, okay? So this also means A or B, or in other words, A union B, all right? All right, so all the elements in B and all the elements in A together, that is the union, all right? Okay, then we say the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A now. And this and means the intersection, right? And we use this upside down U to represent and means the intersection, all right? Okay, and the intersection has to do with what is common between event A and event B. Common. Intersection, simply put, means common, all right? And I'm sure this word intersection is not new, because even in functions, you know, when you have let's say an exponential function, and let's say they have a straight line function, we talk about the intersection of two functions. That's basically where the two functions meet. That's where the functions have a common value. There's a common value, all right, that these two functions share together, all right? So intersection, all right, has, in set notation, the intersection symbol that is used is that upside down U, all right? Upside down. It's no longer U, the proper U, it's the upside down U, and this stands for and. So A and B, the intersection of A and B, okay? Right, so this is very important, all right? So this is what we call the addition rule of probability. The probability of A or B, remember, or means union, and in set notation, we can write or as the symbol U. The probability of A or B is equal to the probability of A, so the probability of A alone plus the probability of B minus the probability of A and B, okay? And this is the alternative way in which we can write the addition rule. So when you see these U's and this upside down U, just understand, oh, the U stands for or, and the upside down U stands for and the or means union, the and means intersection. What is union? Union is like everything we have together. It's like the total sum of elements for A with B. And then and means what is the common elements between A and B. That's very important. So intersection and union mean different things. Union means the total of everything that is there between A with B. But here, intersection means what is common between A and B. Okay? All right. I hope we understand that rule, the addition rule, a very important rule, a rule that we need to understand and know at the grade 10 level, the grade 11 level, and the grade 12 level. So please, guys, let us understand that rule. Okay. Then we have something else that we refer to as the complementary rule. The what? The complementary rule, right? The complementary rule of probability. Okay, so here is the thing about the complementary rule. We say that the probability of A is equal to 1 minus the probability of not A. Okay, and I know for now you're gonna look at this and be like, huh? Okay, I'm gonna get into it, guys. We're gonna get into it. We're gonna get deep into it. For now, I'm just exposing you to the rule. Okay, so A is A. If we are saying not A, it means that it is not the probability of A. It's something that is not the probability of A. Okay, so that's why we say the probability of not A. Okay. So the probability of A is equal to 1 minus the probability of not A. So alternative notation that is used, my good people, is that we can say probability of 1 minus P, then we say A, and then we have this apostrophe. This apostrophe just is a symbol that we use that means not A. All right, or when we actually pronounce it, we say it's A complement. But that A complement has meaning. It just means not A. So this is an alternative notation that they utilize to say A complement just simply means not A. So we should not be shocked when we see not A and sometimes sing A complement, because these simply mean the same thing. So this is what we call the complementary rule. Okay, we call them what? The complementary rule. Okay, now that is enough about our rules. Okay, now there are what we call the events. We have a different type of events when it comes to probability, and I want us now to zoom in to the type of events that we find in what? In probability. So the first type of event that we have is what we call mutually exclusive events. What do we call it? We call it mutually exclusive events. Okay. So mutually exclusive events are simply this. It's when we have two sets that have no elements in common. We have what? Two sets, or in other words, there's these two events that have no elements in common. So we can say two sets or events that have no elements in common. We refer to those types of events as mutually. Now this word mutually, okay, exclusive events. All right. So these are two sets or events that have no elements in common. In other words, the two events do not what? Do not intersect. There is no intersection. Okay, I repeat. The first type of event we have is what we call mutually exclusive events. What about those events? These are two sets, if we are talking about set notation, but these are events that have what? They have no elements in common. Furthermore, the two events do not even what? They do not intersect. Okay? They do not intersect. So imagine now if I took the addition rule, all right, and I tried to represent mutually exclusive events. Now, first and foremost, A or B, the probability of A or B, let's just write down the addition rule. is the probability of A plus the probability of B minus the probability of what? Of A and B. This is the addition rule. But if I am to apply this knowledge about mutually exclusive events to the addition rule, how does this impact my addition rule? So let's check this out. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. What is this? The union of A with B. What is this? The intersection of the probability of A and B. But what did we learn here? That for mutually exclusive events, the two events have no elements in common. In other words, the two events do not what? Intersect. So in other words, there is no intersection. So if there's no intersection, guys, what does that then imply about the probability of A and B? What then can we say about the probability of, if there's no intersection at all, then does this probability of A and B even exist? If there's no intersection, what is the value of the probability of A and B? All right, because we are told that for mutually exclusive events, the two sets of events have no elements in common. In other words, the two events do not what? They do not intersect. If they do not intersect, what is the intersection value? Okay, so I like what Malaudzi is saying, and Nez is saying, Malaudzi with a question mark says, is it 0? Nez, on the other hand, is like confidently saying there's no question mark, is saying it's 0. And this is exactly the truth, guys. The probability of A and B is equal to 0. But this applies to what? To mutually exclusive events. Why do we say that it applies to mutually exclusive events? It's because from the definition, we're saying that the two sets of events have no elements in common. So in other words, the two events do not what? They do not intersect. If there's no intersection, that speaks to, remember, what did we say A and B stands for? What does the N stands for? It stands for intersection. What is common? Is there anything that is common for mutually exclusive events? There is nothing that is common. So if there's nothing in common, what does that mean about the probability of A and B? Okay, so rightfully, as Nez and Malaudzi have said, the probability of A and B is equal to 0. I fully agree. So this is something that you need to note about mutually exclusive events. And this forms part of our conceptual understanding for mutually exclusive events. We know that for mutually exclusive events, the probability of A and B is equal to 0. So in the addition rule, let's go back to the addition rule. How does that affect our formulation of the addition rule for mutually exclusive events? It means the following. We can simply write that the probability of A and B, and I'm going to say for mutually exclusive events, my addition rule will look like this. The probability of A plus the probability of B minus, remember the probability of A and B, that will be 0. So the formula of the addition rule is simply PA plus PB. PA or B is equal to PA plus PB for mutually exclusive events. So the minute you hear this word, understand that your addition rule gets affected at the intersection. Why? Because two sets of events that have no elements in common, the two events do not intersect, no intersection, probability of A and B equal to 0. That's what we know about the mutually exclusive events as it applies to the addition rule. that P A and B is 0, so therefore this is the addition rule formulation of the mutually exclusive events. Okay, yeah, I hope we are feeling this together. All right, then of course we could use our set notation, alternative notation. Remember, or means the U equal to PA plus PB. I love chaos venom. Funzani zinja. All right, you can see a chaos venom. The profile picture has a dog there in the profile picture, and I think it's a symbol of his or her identity, chaos venom. I think he obviously means well by the comment, so we can take that comment very positively. Thank you so much, Funzani Chaos Venom Zinja. We really appreciate your comment. You are the best. You are the best ever in the world, in the whole entire world. We love you. We love you so much. Keep on motivating others in their live sessions, my leader. Okay, I hope we are together here though. The probability of A or B is equal to the probability of A plus the probability of B. For what? For mutually exclusive events. This is the application of mutually exclusive events. Because we know that P and B is equal to 0, the addition rule is affected as such. Let's never forget this. Very important. Very, very important. Okay, they don't bark at stationary cars. You know what I mean, guys. They don't bark. Dogs don't bark at stationary cars. The car has to be moving in order for the dogs to bark. All right, I think it's very key, that thing. All right, let's move on to the next type of event, guys. I hope we all understand mutually exclusive events. All right, and the fact that two sets of events that have no elements in common, the two events do not intersect. So if there's no intersection, probability of A and B is 0, and therefore in our addition rule, PA and B is affected, it is 0. So therefore our addition rule for mutually exclusive events is simply PA or B is equal to PA plus PB. We don't have to worry about PA and B minus PA and B because it is 0. So therefore we know most. We know alternative notation. If we don't write or, we know most. Hi guys, hi. Ieza, it's coming. Woo. All right. Now I want to expose you to something here in grade E. All right. I want to visually show you using a diagram. All right, a diagram. All right, the diagram that we are going to look at is a diagram that has a rectangle, all right, and then these two circles. Guys, when you look at this, what does it remind you of? I don't know if there's anyone that has association when they see this. Do you see anything? Please don't think mathematics. Just like when you look at this, what do you guys see? I want to see the creative people in our language. Just I want to tweak your brain. Just want to check, what do people see? Landy is like Lego blocks. Okay, I love that. I love that. Okay, I'm gonna write that down. Lego blocks. Landy for president. My goodness. Okay, anything else, guys? Okay, I saw the Lego blocks. I love the Lego blocks. Okay, yeah, that gives me like some creativity for days. New names to be given to, I'm going with Lego blocks. I love the Lego blocks idea. I don't know, is there anything else that people see with this? Okay, thank you so much, Landy. We really appreciate the idea. Okay, so guys, this rectangle, all right, represents what we refer to as our sample space. You see? And we use S to denote sample space. So usually they don't write sample space the entire wording, but they usually write S, okay, because the rectangle represents the sample space. So that's the rectangle. Okay, then you have two circles inside, all right, the rectangle. Now this circle is what we call a set in set notation, but we refer to it as an event. This is an event, all right? So since we are dealing with A or B, we are going to say this is event A, all right, the first circle, and then we're going to call this event B, the second circle, all right? We're flowing together now. Are we together so far? All right, so this is event A, this is event B, all right? So circle number 1 is event A and circle number 2 is event B. Now I'm sure if we are going back to this idea of mutually exclusive events, this event A and this event B are not touching each other at all. A and B are separate events. The two events have no elements in common. In other words, they are not, as it says, the two events do not intersect. There is no intersection. So these two events are what we refer to as, this is a diagram that represents mutually exclusive events. Why? Because indeed there is no intersection, because that is the singular thing that distinguishes mutually exclusive events. It's the fact that there's no intersection. Sihamba sonke, uyasala, usalela. Yeah? Is anyone salaring? Oh, we're not salaring, we are all hambering sonke. You know, we are all pepepe, like Casper Nyovest style, all of us. Are we sure? Are we good? Okay. So this is event A, and then that is event B. We are not salarying. Good. We can't sala, guys. There's no time for salarying, please. All right. Ikani sala ni. All right. All right. So event A, event B, mutually exclusive. Indeed, they are. You can see visually. What do we call these things? We call these things Venn diagrams. We call these boxes with circles in there, with circles inside, we call them Venn diagram. And what is a Venn diagram? It is an illustration. Okay, guys, illustration simply means picture. It's just a big word for picture. It's an illustration of the relationship. That's what a Venn diagram. It's an illustration of the relationship between and among sets, or what we call events, that share something in common or don't. Okay. So a Venn diagram is an illustration of the relationship between and among sets or events, okay, or group of objects that share, group of objects that share something in common, that share something in common, right? That is what a Venn diagram is. A Venn diagram is an illustration of the relationship between and among sets or events or groups of objects that share something in common. Okay, so that is a Venn diagram, guys. This Lego box, so I love Lego blocks. You know, like Landiwe is such Landiwe. I absolutely I enjoy Landiwe and the way that Landiwe thinks. You know, So our Lego block is simply what we refer to as a Venn diagram. So that's some vocabulary for you guys that I'm adding. I will be doing that. I'll be posting this live TikTok, this live video, not on my TikTok account, but on my YouTube account, J Boycotty. Man, some people have funky names, J Boycotty. All right, so I'll be posting that there on the YouTube channel. The link is in my bio, including the link to the WhatsApp channel. The WhatsApp channel will have the clickable link there, you know, the clickable link there. All right, so Boycotty. All right, okay, so I hope we are good so far. All right, Lego blocks are called Venn diagrams. That's the official name that we use. Lego blocks, okay, like Landy was said, are called Venn diagrams. What is a Venn diagram? It is an illustration. What is an illustration? Illustration is just a picture, guys, a visual representation. It is a picture of the relationship between and among what? Sets or events. You know, there's a relationship between A and B. Among sets of events or groups of objects that share something in common. Okay, and what is shared here is the fact that they have no intersection in these two events. All right, but they are in the same sample space, which is beautiful. So our rectangle is a sample space, the two circles are events, and inside the events we can have elements, certain things that are inside those respective events. Okay, Venn diagram. Okay, you do this man. Woo! All right, so I hope we are together, we are in the clear. I just want to show you something here. Let's just say we had two events. This is A and B. Let's say there's A, B, C, then we have D, E, and F. I'm sure you guys can see, guys, you know, that in event A, we have A, B, C. So our elements inside event A are A, B, and C. Our elements inside event B are D, E, F. And if we look at the elements, is there anything that is common between the elements in the respective events? You can see, guys, that this is A, this is B, this is C, this is separate, and this is D, there's E, there's F. So there's nothing common between the elements inside the two events. Are we together? Okay. So this is an example of mutually exclusive. So just allow me to use shorthand there. M exclude. All right. I'm just being lazy right now, guys. This is not what you would write, but I'm just writing that this is a representation of a Venn diagram that has mutually exclusive events because the elements are not common. You know. Then let's look at another one. Okay, so let's just imagine this is as straight as can be. The rectangle is perfectly straight there. So we have event A, that's B, that's C. Let's say there's F, and then there's D, and there's E. So what do we notice this time round? Event A and event B are still what? Mutually exclusive. And what we do have is just a letter that is inside the sample space that is not in the events. All right, so this is still mutually exclusive. All right, it's just another representation of a visual diagram that shows us mutually exclusive. Okay, guys, are we feeling the fire? This maths gamer is on fire. Are we on fire, guys? Because, like, you know, like if we're not on fire, guys, then me just wants to end this live right now, you know. Okay, all right, let's move on to the next type of event. Are you ready for the next event, guys? Are you ready? Gilabile. Fire, hey, it's too hot. Kutle is like, you can see that emoticon, the emoji at the end. Yeah, it's the one. That's the one. That's the one. Okay, next event that we would like to look at is what we call, and I got a message from one learner from one of my groups, and he was saying that I am busy doing preparation for next term 3, and I'm doing probability. Say the concept of this that now I'm writing down, guys, the word here is exhaustive. EXHAU. Okay, let me rewrite this because the writing there is very terrible. Exhaustive event. Okay, it's like exhausted, you know. When you are exhausted, you are tired, you are finished, you are clear, you are pelile, you are just done, finished, feditse, you know. Exhaustive event. Okay, now let me just write what are exhaustive events. All elements. Okay, I hope by now we kind of get the language. Okay, when we are talking about elements, we are talking about what is inside the event. So it's saying all elements in the sample space are what? Are included in both sets or events. Let's read this again together. What are exhaustive events? This thing is saying conceptually all elements in the particular sample space are included in both sets or events. All right, so let's look at a diagrammatic representation of what this means. Rectangle, key sample space, dango. We have event A, we have event B. We have A, B, C, D, E, F. And what is this saying? Exhaustive events, all elements in the sample space are what? Are included in both sets. All elements in the sample space are included in both sets. So let's look at the elements. The elements we have are A, B, C, D, E, F, nothing else. A, B, C, D, E, F, nothing else. A, B, C, D, E, F, nothing else. So A, B, C, D, E, F are all elements. Yes. They are in the sample space. Yes. Are they included in both sets of events? Let's look at the set of the events. We have set A, which is event A. We have set B, which is event B. Are all the elements, my question to you, are all the elements included only in the events? Are they? Are the elements included only in the events, guys? Busisiwe, 10, 11, 12, everyone. Are all elements in the events? Okay, because remember it says all elements in the sample space are included in both events. Is that the situation here? We have element A, we have element B, we have element C. It's in event A. We have element D, we have element E, we have element F, they're in event B. Are there any other elements that are outside the two events? No. Are all the elements in the sample space included in both sets? Yes. Yes. So yes, Landiwe, this is a situation where we can say that this is an exhaustive event. And I love Landiwe's humor there. Landiwe is saying they are tired. So therefore, if the elements, this event is what we call an exhaustive event. Yes, Mulawuzi. All right. And this takes us. Yes. So this is a mutually exclusive event as well. But furthermore, it is a mutually exclusive event which can be classified as exhaustive. Why? Because all the elements in the sample space are included in both sets. Right? There's nothing outside the sets. All right? And this is what makes the exhaustive events exhaustive, because all elements must be in the events. We don't want to see even one outside the event. It must be all in the events. If it's all in the events, then we say that this is called exhaustive. So I love what Mulaudze said, and this is a beautiful observation from Mulaudze. Mulaudze is asking them, say, is this Venn diagram, can it be classified as mutually exclusive? Yes, it can be. But furthermore, we can even say that as this event is mutually exclusive, it is also exhaustive. Why? Because all elements are in the sample space. So maybe we can ask ourselves the question, why do we say this is a mutually exclusive event? It is mutually exclusive. Remember, why? Let's see if people can remember. Why do we say this is a mutually exclusive event? All right. Because now we need to get into the theory of the probability and the rules that we learned. So why do we say this is a mutually exclusive event? I love Mulawuzi. There is no intersection. There is no intersection. And specifically, if we are talking about probability, please tell me. If we are now specifically talking about probability, we can say that what? If there's no intersection, it means that the probability, I want to see. Okay, I highlighted it with green when I was indicating why it is mutually exclusive. Yes, there's no intersection, but for probability, we say that the probability of what and what is what. The probability of A and B. This is our reasoning, guys. Right? And this needs to be a package deal. If they ask you why, classify the following event and give a reason. All right? You classify it. Of course, you classify it. And you say mutually exclusive. But when they ask for the reason, there is no intersection, but you further underscore it by saying the probability of A and B is equal to 0. Right? There is power there. Too much power. Okay? So that's why we say it's mutually exclusive. Now, we need to get behind now. Why do we say it is exhaustive? And the reason why we say, guys, it's exhaustive is the following. The probability of A or B is equal to 1. Okay. This denotes exhaustive events, and I will plug you in as to how we get here. The probability of A or B, meaning the union, okay, the probability of A or B should give us 1. This is what denotes the exhaustive nature of the events. Okay, so this would be the reason for us saying the events are exhaustive. The probability of A or B is equal to what? Okay, let's check this diagram. This is A, this is B. We have A, B, C, D, E, F. All right, and what I want to ask you guys again, okay, that would be S, of course. Right? What can we say about this event? Okay, let's start from whether is this mutually exclusive. Let's start there. Is the event mutually exclusive? Is the event mutually exclusive? Let's start there. Nez, Mulawudzi, Landiwe have a common answer. You know, Nez, Mulawudzi, and Landiwe intersect. Where do these three individuals intersect? Okay, this is like Nez, this is Landiwe, and this is Mulawudzi. Okay, they intersect, both of them. They intersect, all three of them, at this point. Okay, their common answer, which is what? Which is no, it is not. We have Landile, this is Mulawudzi, and this is Nez. They intersect, they have a common answer, which is no. Okay, I asked, is this mutually exclusive? Okay, and the answer is deadbeat no. Why? So not mutually exclusive, I agree. This is not mutually exclusive. What would you say is the answer if you were to answer me? Not mutually exclusive. Okay. Okay. Why is it not mutually exclusive? So why is it not mutually exclusive? The reason is there is an intersection. I love that. There is an intersection. There's actually an element there that makes it such that we have this intersection. Okay, so we would then say, give it power. The probability of A and B cannot be zero. Package deal. Package deal. Package deal. Okay, I hope you see the package, guys. The package deal there. Yeah. You say it is not mutually exclusive. The thing is, we see there's an intersection, and we say the probability of A and B cannot be zero. Please, guys, the reasoning is so important. If you just say I'm mutually exclusive, not mutually exclusive, but you don't supply the reason and you don't understand why you are saying, then that's where the downfall will be. So please, guys, take note of the notation. P and B cannot be zero. That's why we are saying they are not mutually exclusive. Remember, when we said they were mutually exclusive, it's because there was an intersection, and this makes it that much more powerful. The probability of A and B was equal to zero in that particular scenario situation. Okay. All right. Now, next thing, is this exhaustive? Hey, let's check, my friends. Is this exhaustive? Ntwe, A and B, event A and B, are they exhaustive? Okay, let's relook at the definition. All elements in the sample space are included in both sets or events. Is that the case? Are these exhaustive events. Are they exhaustive? Are they exhausted? Is Mulawudzi, Noltando, Nez exhausted right now? Feeling sleepy, eyes starting to shut, you know? You want to be contained within the event of your bed. All of you wants to be contained within the event of your bed, within the confines of your warm bed, you know. So mutually exclusive, we said not. Exhaustive, okay, it seems like people are saying yes. So that means we have something that is common, okay, and that is yes. All right. And the reason why we are saying yes is why. Why are we saying the events are exhaustive for this particular Venn diagram? Why are we saying that, guys? Why? Now I need your reasoning there in the comment section. Why? Why are we saying that? Why? Thank you, Mulawati. All the elements are included in both the sets, guys. Okay. And in summary, events are included in both sets. Beautiful, guys. You guys are flowing with me. All elements in the sample space are included in both the sets. You are with me, man. You are with me. And to summarize that, without really writing this huge sentence, what can we then say about the probability? If we want to just summarize everything that we are saying there in words, that's exactly what we mean. All elements are included in both the sets. Beautifully said. But in algebraic probability set notation, how would we summarize what we mean that the events are exhaustive? What would we write? Okay, to just summarize. You know, we would just say the probability of A or B is equal to 1. That's it. Just summarize like that. No big words, no long sentences, or no long phrases. Just to the point. Exhaustive events. Why? Probability of A or B is equal to 1. Okay. Right. Okay. Then I'm now going to touch on the last type of event, so that we can now sort of like at least, you know, have the meat. I am hoping that, hey, if that learner was here, there was a learner, you know, that sent me a message and was like, I don't understand this exhaustive events thing. All right. And maybe let me take it up a notch, this thing, so that you guys can understand why we are saying P or B is equal to 1. Maybe some of you are like, I don't even get this. Why is P or B equal to 1? Why is the probability of A or B equal to 1? Right. So I want us to understand why we are saying the probability of A or B is equal to 1. Do you want me to explain that, or do you guys think that it's fine? Let me just check with you. Do you need me to explain? You guys understand P and B, why you're saying P and B cannot be 0. Do you want me to explain why we're saying the P or B is equal to 1? Before I jump into complementary events, or are we good? I can just go to complementary events. What does the term field? Okay, yeah, Landio is like saying yes, please. So, okay, let's explain it just quickly. And I hope that we do not lose each other in the midst of me explaining. So let's come here. I want us to go back to the idea of probability as per the definition. Remember, probability is simply of a particular event is simply the number of elements in that particular sample space over the total possible outcomes. In other words, the number of elements in the event over the number of elements in the sample space. Now, this one Maybe some of you are going to be like, hey, but how did they get 1? Listen, and listen very well. All right. So there is generally 2 ways, all right, that we can look at this. Remember, I explained what or means, all right? The probability of A or B. What does or mean? Do you guys remember what I said the word or means? Or means, I'm gonna wait for you guys to tell me, because in that lies your understanding. Okay, Landiwe says union. And then in layman terms, do we understand what we mean by union? Do we understand what we mean by union? So if we're saying A or B, this is event A or event B. What are we saying about the elements in these respective events? Very good, Landiwe. Together. Okay. United. I love that. Sum. Yeah, well, when you say together, it's like all together. And all together means the sum. Okay? So I hope you guys understand that. It's like the sum of the elements. So I'm going to write that. The sum of the elements in the 2 events. Sum of elements in the 2 events. So if we look at this in that way, I want you to understand this very well. Very, very well. Please understand this very, very well. Okay? If we look at the definition of probability, if we were to say, what is the probability of A or B? The probability of A or B will simply be the number of elements in A or B over the number of elements in the sample space. Are you guys with me? I'm going back to the basic definition of probability. What is the probability of a particular event? Probability of a particular event is the number of elements in that event over the number of elements in the sample space. Okay? So, what's the probability of A or B? Probability of A or B is equal to the number of elements of A or B over the number of elements in the sample space. Right? So let's come here. Right? We had declared and concluded that this is an exhaustive event because the probability of A or B is equal to 1. Let's check if it actually is equal to 1. What is the number of elements of A or B? Remember, what did we say mean the or means? It means the union. What does union mean? It means together, the sum of elements in the 2 events. So let's look at the elements in the 2 events. How many elements do we have inside the 2 events? How many elements do we have inside the 2 events? What's the total number, right, of elements for the 2 events? Very good, Landiwe. We have A, B, C, that's 3. D, E, F, that's another 3. That's 3 plus 3, which is equal to what? To 6. So if I was to talk about the number of elements for A or B, meaning the union of A or B, in other words, the sum, the united number of elements for A or B, we are counting 1, 2, 3, 4, 5, 6. Okay. Zebertu root, I don't know if maybe your numbers are upside down, my leader. I have a feeling you are upside downing things, but we'll forgive you. So the number of elements, you guys are correct. It is 6. Okay. Thank you so much, Zebertu root. You have just fixed your mistake. Very good. Then, what is the number of elements in the sample space? Okay. Remember, the sample space is the entire what? Triangle. Yo, I'm saying triangle. What nonsense am I saying? I think I'm being affected here. The entire rectangle. So elements in the rectangle, how many elements do we have in the rectangle? The total number of elements in the rectangle. How many do we have? Because that's the number of elements in the sample space. How many do we have, guys? How many elements do we have in the entire sample space? Okay, so obviously the sample space will include all the elements inside the rectangle, and in the rectangle there's the elements in the circle as well. Does that make sense? So outside the circles there's nothing, inside the circles there is something. In total we have how many elements? 1, 2, 3, 4, 5, 6. There's no other external elements outside the two circles. So in total, how many elements do we have in the sample space? We have 6. Okay, all right, so hopefully we are together. Nez, please, hopefully we are together. Okay, what is 6 divided by 6, guys? No, Landiwe. Remember, elements are not the circle. The circle represents what? Remember, what did I say the circle represents? I said the circle represents an event. The elements are inside the circle or outside the circle. All right, so in this situation, okay, we do not count the circles as elements. Please, ne? Let us be together there. So 6 divided by 6 is equal to 1. Now, don't you see that PA or B is equal to 1? It is. So for exhaustive events, we are 100% correct when we say that all exhaustive events, for all situations where you have a Venn diagram where all the elements in the sample space are included in both sets of events, you are bound to get a situation of where the probability of A or B is equal to what? To 1. Do we understand? Siyavana, siyaqonda, akutlisisa, ankushisha. All right, so we're together. All right, Mulawet, we are going there. Well, now we are here, Mr. Mulawet. All right. I hope is it Mr. or Mrs. Mulawet there. I'm making a mistake. Maybe I'm thinking of KK there in Muvango. KK Mulawet. You see, now I'm thinking it's Miss there as well. If it's Miss, I'm sorry about that. So guys, here, oh, it's Miss. Okay, sorry, Miss Mulawet. How could I butcher? Right. So here, let's look at this. You remember here we said these are also exhaustive. All elements are in the events. So once again, we are going to look for the probability of A or B by counting the elements in the sample space. Right. P, A, or B is equal to the number of elements of A or B, meaning the union, what we have together. So the number of elements for A or B, what would we say? The union is, how many elements do we count for A or B? Number of elements, A or B. The union, what we have all together for A or B. What is the number, guys? Give it to me. I'm listening. Number of elements, A or B. Mulawet says 6. Nez says 6. I love it for yourselves, guys. You see 1, 2, 3, 4, 5, 6 in the events. Right, so the number of elements of A or B will be 6. Then we look for the number of elements in the sample space. So what about the sample space now? What about in the sample space? Number of elements in the sample space. How many? It is still 6. And then what is 6 divided by 6, guys? I'm telling you, shoot dirty money. I'm telling you, shoot it, guys. I'm telling you, shoot. Shoot. 6 divided by 6 is 1. You see? Okay. So the probability of A or B, even in this scenario, gives us what? 1. Which makes sense that these are exhaustive events as long as all elements in the sample space are included in both the sets. Then we say the events are exhaustive. And we underscore it by saying the probability of A or B is equal to 1. We don't have to calculate it. It's just that I am showing you where the 1 comes from so that you guys move on in your heads with a conceptual deep understanding of why we conclude and we write this as our package deal answer. We say exhaustive events, and this is our reason for saying they are exhaustive. P A or B is equal to 1, because in any situation where the elements are in the sample space included in both the sets entirely, you are always going to get the probability of A or B being equal to 1. In other words, the union of the two events, its probability will give you 1 all the time. You guys saw it when the events were mutually exclusive and the elements were in the respective events, and you saw it when the events were not mutually exclusive but still the elements were in the events. You saw that the answer is giving 1. Comrades, shoot me, shoot. Okay, I don't know if there's any questions, but maybe now I can move to the last event for the night, and then I can let people be continued tomorrow, the next segment. And we're just gonna do the last type of event, guys. The last type of event. For me, the conceptual understanding is very important. When you understand the concept, you have knowledge and you have understanding, and then you are able to actually maneuver when questions come, because you understand what you are dealing with. You understand this thing. All right. I'm learning shooter, guys. Complementary events. What are complementary events? Take note. The events are complementary. Okay, complementary. Spelling complementary. Events. It's not the first time you're seeing this word complementary. I'm sure you've seen complementary when you're doing geometry in term 2. Angles that add up to 90 degrees are called complementary angles. So this is a word that you've seen before. But now we are not talking about complementary angles. We are talking about complementary what? Events. Landy, oh my soul. Don't I just need you like in my teaching life? I wish I had a Landiwe brain when I teach, so that I can just, have the switch that comes on whenever I'm talking about certain things. So thank you so much for that. The events are both, if the events are both 1, exhaustive, and 2, mutually exclusive, then they are what? Then they are complementary. So if this particular thing that we have has both mutually exclusive and exhaustive, then we say that the events are complementary. The events are complementary. Okay, the events are complementary. Exhaustive and mutually exclusive. So let's think about this practically. Let's think about this practically. If you have the addition rule, remember the addition rule? You remember it, Mosne? Okay, you remember the addition rule. When an event is mutually exclusive, we know that PA and B is what? Let me see if people still remember. When an event is mutually exclusive, why is it again that it's mutually exclusive? It's because of what? Alright, I love Inez, thank you so much. PA and B, it's when P and B is equal to 0. So already I'm seeing that say bye bye, say bye bye, say bye bye, say bye bye, yeah, say bye bye. I can already see P and B saying say bye bye. And then so mutually exclusive, direct application gone, right? Then exhaustive. What did we say when events are exhaustive? It means what exactly? Does you remember? When they're exhaustive, we say what exactly? When the events are exhaustive, let's remember there was a combo deal. Events are exhaustive, right? Let's not forget this. POB is equal to 1. If the events are exhaustive, then PA or B is equal to 1, right? Let's not forget this, guys. Very, very important. Okay. Yes. Okay. And please be careful. Mutually exclusive, PA and B, the intersection is equal to 0. But if it's exhaustive, it means the union, the probability of the union is equal to 1. So in other words, PA or B is equal to 1. That's one of the things we don't want to confuse. Okay. Then PA or B, that means in the addition rule, we're also going to say bye-bye to PA or B. We are going to write in the place of PA or B 1. Then we have PA plus PB, and then obviously here say bye-bye. Okay, so after all is said and done, for complementary events, this is simply saying that PA plus PB is equal to 1. This is what we mean by complementary events. All right, and this is where I'm going to stop for today. Right, guys, we've covered quite a bit because this is a lot of theory. Okay. And what I want you then, guys, to do is that I'm going to obviously download this video, go and upload it onto my YouTube channel. Maths is a Game. We know the link is in my bio. You can find it there. The 2 videos of the live lessons that I've done, the 2 previous nights, are already uploaded onto my YouTube channel. It's the 2 most recent videos I uploaded. For probability, first video is kind of up to like roughly an hour nearly, then the second video is like roughly 2 hours, and then this one now, don't know how long it is, but it's quite long. Okay, and then what you can do, guys, is you can actually go and rewatch. Those who came midway, you can go and check out from the beginning so that you can actually move with the content from the beginning as I was explaining it. Okay, it's quite a bit that we did because today we're focusing primarily on the general rules of probability, starting from the basic definition of probability to the addition rule of probability, the complementary rule of probability. Then we looked at these events and explained them even through Venn diagrams. You have mutually exclusive events, We looked at the Venn diagram with the addition rule and how that affects the addition rule, since we know the probability of A and B is equal to 0 for mutually exclusive events. Then we looked at exhaustive events. Okay. Then we looked at complementary events. And this is where we are ending for tonight, right? No problems, no exercises, just the conceptual basic understanding of these, all right? Yeah. Remember, like I said, UML 255. Okay, I am fundamentally posting after I'm done the sessions onto my YouTube channel. So you have then the prerogative or the responsibility of going to the YouTube channel if you've missed, and then watching or rewatching the live. All right. So guys, I think I'm gonna actually standardize the time and put the evening time, because I can't do live sessions during the day. Unfortunately, you know, my time does not allow me to. I'm also involved in winter classes, actually starting tomorrow up until the 11th. I'm physically going and doing winter classes for learners this holiday. So I am not going to be able to be available on the daily to assist, but when I can, you'll just see by the live. And then, like I said, I post the videos so that people can rewatch at their own time, of their own convenience. So let me encourage those who have probably only joined, like seen the live today, and they're like, what is happening here? Seems interesting. I'd love to be ahead as well with my term 3 work, you know, like I mean. So why are you leaving me behind? Well, I'm not leaving you behind, more than I'm like just moving. But I'm uploading, guys, on the YouTube channel. You can see the video. You can rewatch on your own time. All right. Stop and pause. You can always come here and ask me questions if you feel like there's something you missed. You can even request the guest request me. You can come onto the live. I can chat to you if there's something that you want clarity about. That's something that's available. It's a means through which we can be able to engage on certain things here. Okay, so I'm gonna end here on this note. Thank you so much for joining in. I will be live again tomorrow evening, and it will most likely be 9:30, if not 9 o'clock. All right, and we will see how far into the continuation of this topic probability we can go into. And remember, guys, that the minute I finish this probability, then we will be able to move on to other topics that Term 3 has to offer, because I'm going to take this one step at a time. And yes, I'm inviting all grades to come to the session all at once, like grade 10, please be here. This is relevant for grade 10, it's relevant for grade 11. Grade 12s need to be in the attitude of revising. So for instance, tomorrow with the session, grade 10, grade 11, grade 12. If you are in grade 10, grade 11, grade 12, the session tomorrow, the continuing session on probability for tomorrow will be beneficial for all grades. So don't have this thing that, some grade 12s will quickly pick up from what I'm doing, that he's doing grade 10 or grade 11 level content or grade 10 content. But please do join. When I want people to not be in the live session, a specific grade not to be here, I will tell you that, hi guys, grade 10s, can you excuse yourselves, because this is relevant only for grade 11 level. Okay, but for now, I want everyone to be here. Tomorrow, I want everyone to be here, because it's good revision for grade 11s as well and grade 12s. But grade 10 is the first time, so that's why I'm taking it slowly and nicely with you guys. I'm explaining definitions, I'm explaining concepts, so that you guys can be on board. And if you have questions, please don't fear. You can just go there to the guest thing and request, and I can talk to you live, and you can ask your question and express your concern, so that we can clarify things that are not clear for you. All right? Any $1 million questions before we leave each other and we call it a night of nights? Before we say bye-bye, say bye-bye, say bye-bye, say bye-bye. Eh? Doom, 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 doom. Doom, doom, doom. Eh? No questions. Okay. All right. Then that means things were clear. Thank you so much, guys. It was really, really nice having you guys. And Bertu wrote, great having you. If it's your first time, well, welcome to the team. This is what we call the Maths is a Game platform. Maths gamers, we play very hard. We learn the concepts, we do the things, and we are just in it for the love of it. Okay. Lwazi, conditional probability for the syllabus that is the high school syllabus for CAPS is actually not inclusive or not examined or included in the grade 10, 11, and 12 syllabus, according to the CAPS documents and the exam guidelines. So conditional probability is not really tested. So yeah, and I am teaching learners within that CAPS framework. You know, of course, I do understand that if you maybe are doing IEB or maybe you are doing other extended conceptual maths concepts, then of course you'll be exposed to something like conditional probability and its application. But here, not so. Okay. Thank you so much. And like I said, guys, if you've missed all the other videos, you can more than go and the YouTube channel, guys. The link is in my bio. It's also called Maths is a Game 5 to 7. Just check it out. You can go and watch the recent videos that I uploaded of the live sessions. 2 live sessions already done and dusted. This will be the 3rd. I'll be trying to download the session so that I can upload it onto the YouTube channel. You can watch it at your own time. And then you can be caught up. If you have questions for me, be free to ask and get clarity. Thank you so much. Greatest love. Have a great night. Maths gamers. Thank you so much. Yeah. The end. Say bye-bye. Say bye-bye. Say bye-bye.